That means if I have actual ellipses, not circles, then the gradient doesn't exactly going to it's not going to exactly point towards the maximum direction, towards the local towards the maximum. If you, for example, if you look at in this case, we have a ellipsoid, but let's say I think the origin is a little bit too close to the optimal for us to see. So let's actually try a different b. So my b is actually pretty small. So let's say is equal to b times 10. So let's multiply. Uh, let's make the linear term a little bit bigger for us to actually see. I'm going to redo the calculation and close and plot another contour. Okay, so now we have a different contour. Let's grid, right? And if I start at the origin, which is the center point of this contour, center point of this plot, we can see that if you refine, let's actually draw the contour with a little bit more levels. So let's draw it with 50 different levels. Okay, so now if you start from the origin, and you can imagine I have a gradient direction that actually in this case it points towards the upper right corner, right? It points uphill, right, towards the red region. But which means if you want to minimize the function, you should actually go towards the negative gradient direction, which is going towards the lower left. And you can easily see that you are not going to go towards the minimum of this function, right? The minimum of this function actually lies on your lower right? So it's somewhere here. So if you want to look at it, we can compute the S star here and hold on and plot it. Right, so the minimum actually lies over here. It's almost straight down and slightly to the right. If you follow the negative gradient direction, you follow just locally which direction is going to lead you to a lower value, you would be working towards the lower left. That is when this Hessing, right? This Hessing becomes useful. You are not actually taking S star equal to just the negative G. You are inverting the Hessing and use the inverse of the Hessing to direct you towards the correct minimum. All right. So this formula is actually going to be very useful, not just in the quadratic case, but also it's going to be useful in the more general case. So now equipped with how do we optimize a quadratic in a multiple variate case, we can now think about how do we optimize a general function. So a general function is a function that is not a quadratic, but we want to optimize a function that is smooth. Okay, so when a function is smooth, we can have Taylor series expansions, right? So if we have Taylor series, well, we can think of what order we can expand it to. So the simplest one is going to be a constant. J of S is equal to, let's say we pick a reference point, let's say S0. S0 can be our initial guess on the optimization, right? If we want to optimize an airfoil, we can choose our initial guess to be some kind of a standard airfoil, like NACA 12. So that's going to be our initial guess. So that's going to be a 0th order Taylor series approximation, which may be useful elsewhere, but not really useful in optimization, right? It's not going to be It's not going to help us figure out what S is best. So let's try go to our next level. Our next level is a first order approximation J of S0 plus the derivative of J with respect to S at S0 times delta S, right? So where delta S is equal to S minus S0. So that's a first order Taylor series approximation. Now, this is somewhat useful for optimization, right? Because now at least the function approximation varies as I use different S's. But it's not going to tell me what S is actually going to be optimal. It's going to tell us a direction, right? It tells us, okay, if I make my delta S, if I increase or decrease my S in particular directions, is that going to increase or decrease my objective function? But it's not going to tell me how can I choose the S that is going to lead me to an optimal answer. All right. Okay. So what we want to do is we use a second order approximation. That's where our quadratic becomes useful. So if we use a second order approximation, my S and my J can be approximated as a constant term plus this linear term, right? That is related to the gradient, and then plus a Hessing term plus a second order term. That is a half, as in our univariate Taylor series. Now we are doing multivariate Taylor series. Delta S transpose times the Hessing, the second derivative of H, with respect to S at S0 times delta S. So again, delta S is equal to S minus S0. So that's our second order Taylor series expansion. Okay. This now is useful because once we made this approximation, we can figure out what delta S should we choose to maximize or minimize this second order approximation. How do we do that? We choose delta S equal to the solution of the quadratic optimization problem we used we looked at in the last slide, right? So that is delta S equal to minus sorry, this is second derivative of J, which is usually written as H. It's equal to minus of the Hessing inverse times the gradient, right? Or sometimes written as minus H inverse times G, right? So where this is the second derivative is denoted as H, the Hessing, and the first order derivative is denoted as G, the gradient. Okay,